Yes, using a 24 volts DC relay on 24 volts AC can cause problems. Firstly, coil heating may occur. Alternating current voltage causes the relay coil to heat up due to the changing magnetic field. Since the relay is not designed for alternating current voltage, it may overheat and fail prematurely. Secondly, reduced coil current can happen. The alternating current voltage causes the coil current to vary continuously, leading to reduced magnetic force and lower holding power. This can result in unreliable operation. Thirdly, contact arcing is possible. The alternating current voltage breaks the circuit multiple times per cycle, causing arcing at the contacts. This arcing can damage the contacts over time, reducing their lifespan and reliability. Shorter contact life occurs because the contact life of a relay designed for direct current voltage is typically shorter when used with alternating current voltage due to the arcing and heating effects. Lastly, coil buzzing may be heard, as the alternating current voltage can cause the relay coil to buzz or hum due to the changing magnetic field. This noise can be annoying or interfere with other electronic devices. Therefore, it is not recommended to use a 24 volts DC relay on 24 volts AC. Instead, use a relay specifically designed for 24 volts AC operation to ensure proper functionality and reliability. When dealing with electrical components like relays, it's crucial to understand their specifications and limitations to ensure safe and reliable operation. Relays are electromechanical switches that use an electromagnetic coil to control the opening and closing of electrical contacts. They are widely used in various applications for switching circuits, controlling motors, and providing electrical isolation. A direct current relay is designed to operate with a direct current voltage applied to its coil, while an alternating current relay is designed to operate with an alternating current voltage applied to its coil. The fundamental difference lies in how the magnetic field is generated and sustained within the relay's core. In a direct current relay, a constant direct current voltage is applied to the coil, creating a steady magnetic field that attracts the armature, causing the contacts to switch. The magnetic field remains constant as long as the direct current voltage is applied. In an alternating current relay, an alternating current voltage is applied to the coil, creating a changing magnetic field that alternates its polarity with the frequency of the alternating current voltage. The alternating magnetic field induces eddy currents in the core, which can cause heating and vibration. The design of an alternating current relay takes these factors into account to ensure reliable operation. When a direct current relay is used with an alternating current voltage, several problems can arise. The changing magnetic field caused by the alternating current voltage induces eddy currents in the relay's core, leading to increased heating. The direct current relay is not designed to dissipate this heat effectively, which can cause the coil to overheat and potentially fail. The alternating current voltage causes the magnetic field to fluctuate, reducing the holding power of the relay. This can lead to unreliable operation, especially when the relay is used to switch heavy loads or in applications where consistent contact is essential. The fluctuating magnetic field can also cause the relay to vibrate, generating audible noise known as coil buzzing. This noise can be annoying and may indicate a problem with the relay or the circuit it is connected to. The alternating current voltage can cause arcing at the contacts when they open and close. This arcing can damage the contacts over time, reducing their lifespan and reliability. Direct current relays are typically not designed to withstand the effects of arcing caused by alternating current voltage. To avoid these problems, it's essential to use a relay that is specifically designed for the type of voltage being used. Alternating current relays are designed to handle the effects of alternating current voltage, such as eddy current heating, fluctuating magnetic fields, and contact arcing. They typically have features like laminated cores to reduce eddy current losses, shading coils to improve holding power, and arc suppression mechanisms to protect the contacts. When selecting a relay, it's crucial to consider the voltage, current, and contact configuration required for the application. The relay's voltage rating should match the voltage of the circuit it will be connected to, and its current rating should be sufficient to handle the load being switched. The contact configuration should also match the application's requirements, such as normally open, normally closed, or single pole double throw. In addition to voltage and current ratings, it's also important to consider the relay's operating temperature range, mechanical life, and electrical life. The operating temperature range specifies the range of temperatures within which the relay can operate reliably. The mechanical life specifies the number of operations the relay can perform without mechanical failure, while the electrical life specifies the number of operations the relay can perform at its rated voltage and current without electrical failure. When replacing a relay, it's crucial to choose a replacement that meets or exceeds the specifications of the original relay. Using a relay with lower voltage or current ratings can lead to premature failure or even hazardous conditions. In summary, using a 24 volts DC relay on 24 volts AC can cause several problems, including coil heating, reduced coil current, contact arcing, shorter contact life, and coil buzzing. To ensure proper functionality and reliability, it's essential to use a relay specifically designed for 24 volts AC operation. When selecting a relay, consider the voltage, current, and contact configuration required for the application, as well as the relay's operating temperature range, mechanical life, and electrical life. Always choose a replacement relay that meets or exceeds the specifications of the original relay. Understanding the differences between direct current and alternating current relays and their respective applications is crucial for ensuring safe and reliable operation in electrical and electronic systems. Remember to always consult the manufacturer's specifications and guidelines when selecting and using relays. Electrical components should be installed by qualified personnel. Ensure that the power is disconnected before working on any electrical circuits. Always use appropriate safety precautions, such as wearing insulated gloves and eye protection when working with electrical equipment. By following these guidelines, you can help ensure the safe and reliable operation of your electrical and electronic systems. Now, let's delve a little deeper into the technical aspects of relays and their behavior under different voltage conditions. We'll examine the underlying principles that govern their operation and the reasons why using a direct current relay on an alternating current circuit can lead to the issues we've discussed. At its core, our relay is an electromechanical switch. It consists of a coil of wire wrapped around a core material, typically iron or steel, and a set of contacts that are mechanically linked to an armature. When a voltage is applied to the coil, it generates a magnetic field that attracts the armature, causing the contacts to switch from one position to another. In a direct current relay, the applied voltage is constant, resulting in a steady magnetic field. This magnetic field exerts a force on the armature, pulling it towards the core and closing or opening the contacts depending on the relay's configuration. The strength of the magnetic field is proportional to the current flowing through the coil, which in turn is determined by the applied voltage and the coil's resistance. The design of a direct current relay is optimized for this steady-state operation. The core material is chosen to provide high permeability, allowing for a strong magnetic field to be generated with a relatively small current. The coil is designed to minimize resistance, reducing heat generation and maximizing the magnetic field strength. The armature and contacts are designed to provide reliable switching and low contact resistance. When an alternating current voltage is applied to the coil of a direct current relay, the situation changes dramatically. The alternating current voltage causes the current flowing through the coil to vary sinusoidally with time. This, in turn, causes the magnetic field to alternate in strength and polarity. The alternating magnetic field induces eddy currents in the core material. Eddy currents are circulating currents that flow within the core due to the changing magnetic field. These currents dissipate energy in the form of heat, which can cause the relay to overheat. The heating effect is more pronounced at higher frequencies of the alternating current voltage. The alternating magnetic field also affects the armature's behavior. The armature is now subjected to a fluctuating force that alternates in direction with the frequency of the alternating current voltage. This can cause the armature to vibrate, generating audible noise or buzzing. The fluctuating force can also reduce the holding power of the relay, making it more susceptible to accidental switching or contact chatter. Contact chatter refers to the rapid opening and closing of the contacts, which can cause wear and tear and reduce their lifespan. Another issue that arises when using a direct current relay on an alternating current circuit is contact arcing. When the contacts open or close, a small amount of current can continue to flow through the air gap between the contacts, creating an electrical arc. This arc can damage the contacts by eroding the contact material and causing oxidation. Direct current relays are typically not designed to handle the effects of arcing caused by alternating current voltage. Alternating current relays, on the other hand, are designed to mitigate these issues. They often have laminated cores, which are made up of thin layers of metal insulated from each other. This reduces the flow of eddy currents and minimizes heat generation. They may also have shading coils, which are small coils placed strategically around the core to improve the holding power of the relay. Shading coils create a magnetic field that is out of phase with the main magnetic field, which helps to stabilize the armature and prevent chatter. Furthermore, alternating current relays often have arc suppression mechanisms such as capacitors or varistors to protect the contacts from arcing. These components absorb the energy of the arc, reducing the damage to the contacts. In conclusion, using a direct current relay on an alternating current circuit can lead to a variety of problems, including coil heating, reduced holding power, contact chatter, and contact arcing. These problems can reduce the relay's lifespan and reliability. To ensure proper operation, it's essential to use a relay that is specifically designed for the type of voltage being used. Always consult the manufacturer's specifications and guidelines when selecting and using relays. Always prioritize safety when working with electrical components. Ensure that the power is disconnected before working on any electrical circuits. Use appropriate safety precautions, such as wearing insulated gloves and eye protection when working with electrical equipment. Now let's consider a real-world example to further illustrate the importance of using the correct type of relay. Imagine a scenario where a 24 volts DC relay is used to control a lighting circuit powered by a 24 volts AC transformer. The relay is intended to switch the lights on and off based on the signal from a motion sensor. Initially, the relay may seem to function correctly, switching the lights on and off as expected. However, over time, the issues we've discussed will begin to manifest themselves. The relay coil will start to overheat due to the eddy currents induced by the alternating current voltage. This can cause the insulation on the coil to break down, leading to a short circuit or complete failure of the relay. The contacts will also start to degrade due to the arcing caused by the alternating current voltage. This can cause the lights to flicker or fail to turn on at all. The buzzing noise from the relay will become more noticeable, indicating a problem with the relay or the circuit it is connected to. Eventually, the relay will fail completely, leaving the lights either permanently on or permanently off. This failure can disrupt the operation of the lighting system and may even pose a safety hazard. To avoid this scenario, it's essential to use a 24 volts AC relay instead of a 24 volts DC relay. An alternating current relay is designed to handle the effects of alternating current voltage, such as eddy current heating, fluctuating magnetic fields, and contact arcing. It will provide more reliable operation and a longer lifespan. In addition to using the correct type of relay, it's also important to ensure that the relay is properly sized for the application. The relay's voltage and current ratings should be sufficient to handle the load being switched. Using a relay with lower voltage or current ratings can lead to premature failure or even hazardous conditions. It's also important to consider the relay's operating temperature range, mechanical life, and electrical life. These specifications will help you choose a relay that is suitable for the specific application and operating environment. Remember, electrical components should only be installed by qualified personnel. If you are not comfortable working with electrical circuits, it's best to consult a qualified electrician. Always disconnect the power before working on any electrical circuits. Always use appropriate safety precautions, such as wearing insulated gloves and eye protection when working with electrical equipment. By following these guidelines, you can help ensure the safe and reliable operation of your electrical and electronic systems. Now let's consider some additional factors that can affect the performance and lifespan of relays. One important factor is the type of load being switched. Resistive loads, such as incandescent lights or heating elements, are relatively easy on relays. They draw a steady current when switched on and do not generate significant voltage spikes or surges. Inductive loads, such as motors or transformers, are more challenging for relays. They generate voltage spikes when switched on or off, which can damage the relay contacts. Capacitive loads, such as large capacitors or long cables, can also generate voltage spikes when switched on. To protect relays from voltage spikes and surges, it's often necessary to use surge suppression devices, such as varistors or transient voltage suppressors. These devices absorb the energy of the voltage spikes, preventing them from damaging the relay contacts. Another factor that can affect relay performance is the operating environment. Relays that are exposed to harsh environments such as high temperatures, humidity, or vibration may have a shorter lifespan. To protect relays from harsh environments, it's often necessary to use sealed or encapsulated relays. These relays are designed to withstand extreme conditions and provide reliable operation. It's also important to consider the mounting orientation of the relay. Some relays are designed to be mounted in a specific orientation, such as vertically or horizontally. Mounting a relay in the wrong orientation can affect its performance and lifespan. Always consult the manufacturer's specifications for the recommended mounting orientation. Regular maintenance can also help to extend the lifespan of relays. This includes cleaning the relay contacts and checking for signs of wear or damage. If the contacts are dirty or corroded, they can be cleaned with a contact cleaner. If the contacts are worn or damaged, the relay should be replaced. In summary, using the correct type of relay, properly sizing the relay for the application, protecting the relay from voltage spikes and surges, and providing regular maintenance can all help to ensure the safe and reliable operation of electrical and electronic systems. Always consult the manufacturer's specifications and guidelines when selecting and using relays. Electrical components should only be installed by qualified personnel. Always disconnect the power before working on any electrical circuits. Always use appropriate safety precautions such as wearing insulated gloves and eye protection when working with electrical equipment.